we are developing our interface onto existing packages, in some cases, they can share some object names, exactly the same object names. So of course, at compilation time, you can trick a little bit some function names, some subroutine names, adding, for instance, an underscore character or stuff like that. But I don't think this is really efficient, especially when you have to deal with these very large existing packages. So this said, what are the current and future developments of our Tinker QMMM interface? The first thing we would like to achieve is to be able to use all the available force fields, or most of the available force fields in Tinker, including especially the one which are based on multipoles and which are polarizable, because now this is becoming quite of a standard in QMM applications. We also would like to go for periodic boundary conditions using especially eval sums. And in that respect, our ESPF electrostatic coupling method is really, really efficient. And we also would like to go to non-periodic boundary conditions, including some interface between continuum and the QMMM subsystem. Of course, this API I've mentioned with working now only between the QM and MM packages, when the QM is actually the master process. So now we would like to also develop the same API when Tinker is actually the master. And in that respect, we would get access to many flavors of facilities, of properties that are existing into this MD package. And one particularly important aspect of the future developments is that we really would like to go to really fast QMMM MD simulations. And for that, we will switch in during the next few months to a slightly different package, which is the Tinker HP package. This package has been designed for really taking advantage of HPC supercomputers, including GPUs. So in that respect, if we can go to Tinker HP, this will open the way to modeling very large system for very long times. But what could we do with this kind of implementation? So this would be just a couple of slides about science. These last years, we have been interested into pH effects on rhodopsin retinal photo-isomerization. And on that slide, I can give you some example. This is here about this anabinary sensory rhodopsin, which is featuring two different flavors of retinal, either all trans or 13-cis, as you can see here. And depending on the pH, the absorption spectrum maximum of this protein is changing, as you can see here on the black line. You see there are some teeny shifts, a few nanometers red shift going from acidic to pH 5, and then some a little bit larger blue shift going from pH 5 to pH 7. And actually, we have designed a protocol which is based on constant pH molecular dynamic simulations and thousands of QMM calculations, with which we were able to reproduce this trend, as you can see here on the red line. The difference between the red line and the blue line is just about the embedding of the protein. In the red line, we have considered the membrane, whereas on the blue line, this is just the protein in water. And so you can see that actually the membrane matters in that respect, especially when you have to deal with these very small shifts in lambda max. And moreover, we were able to understand the origin of these shifts. For instance, when you go from pH 3 to pH 5, we were able to analyze the origin of this shift by means of separating the contributions of the change of protonation states in different amino acids. And for instance, in that case, it turned out that this particular amino acid, D120, was the main responsible for this shift. And this amino acid, actually, if you look on the left side, this is the one in red here, which is close to the beta iron part of the chromophore. It's not really close to the part where the chromophore is isomerizing, but it's really on the other part, and it has some kind of effect on the destabilizing effect on the ground state of retinal. And we were also able to understand how the change of pH was influencing the electronic structure properties of retinal, but just plotting how the electrostatic potential felt by retinal is changing with the pH, as you can see on the right side. You can see here that, for instance, going from pH 3 to pH 7, the electrostatic potential fed by the beta ion ring is changing a lot from a positive value to a slightly negative one. Okay, so having this kind of model, can we study really the photodynamics of retinal inside that protein embedded in the membrane? So yes, we can. It's a really huge, it's a really large effort that we have to deal with, because we were able to run these semi-classical molecular dynamics simulations for different isomer of retinal in the protein, for different pH values, taking into account the different initial protonation states of the protein. And this is here, for instance, one example of the protein at pH 3 for the ultrans retinal. So starting with a dihedral value close to 180 degrees. And if you see how the trajectories evolve in time, suddenly you have this torsion that decreased towards 90 degrees. The black dots are representing hops between S1 and S0, and then the decay to S0. And then you have also a family of trajectories that remain at the initial value of the dihedral and eventually hop back to the ground state, but being unreactant, meaning that the retinal isn't isomerizing. So we did that at different pH values for the two isomers, and we obtained these results about the quantum yield of isomerization, and we were also able to model the decay of this system thanks to two exponential functions. So the first one, which is a fast decay, emphasized by the tau1 time constant, and the slower decay pathway, which is characterized by this tau2 time constant. So I don't want to go into the details of these values, but it turned out that if you consider pH 7 for the ultrans isomer, the results we obtained were quite surprising. Actually, it turns out that this tau1 time constant is really too slow with respect to what is known experimentally. And so we had, of course, to go back to our model, to our simulations, and try to understand what could be the origin of such a discrepancy. And it actually turns out that because we had to run such a large amount of trajectories, we needed to rely on very low level for the QM package. In that case, it is the Cobram package based on the semi-empirical OM3 Hamiltonian. And it turns out that the potential energy surface for this system at this pH value is not so good. And also, we were obliged to consider the protein as in the gas phase, so we had to remove the membrane. Most of the structure was frozen, at the exception of retinal and in its cavity. So now we would like to do better. Better means faster and of course more reliable. And this is what is motivating our further developments. So I will finish here. I would like to thank you very much for your attention. And as Nicolas said yesterday, we have an open postdoc positions that we would like to fill as soon as possible. Thank you very much.
Thank you. Thank you for a very good, nice talk. So we have roughly 2 minutes. So any question? Yeah, please.
Yeah, thanks for very nice talk. Uh, your first the part of your talk, connecting Tinker with your QM, and your concern was that the communication, a standalone program case communication, is a bottleneck. I mean, the
Yes.
writing the files, right? What would be the size and
What would be
the size of those files, but also if there's any possibility of writing those to the, the main memory rather than hard disk?
for the time being, when the two programs are running separately, we can have a way to make their memory communicating except using these communication files. And yes, you are right. The communication files are huge. Here, if you look at the numbers, there is a standard communication file in red, which is a few hundreds of kilobytes, not so large. But then when you look at the communication file, which is meant really for the second derivatives, then it turns out that it could reach several hundreds of megabytes, even gigabytes. So yeah, in that case, you spend a lot of time just writing that files and then reading that file by the other program. This is really inefficient.
But
So this is a reason why we would like just to go to another format, for instance, HDF5. We could also take advantage of the sparsity of the Hessian matrix.
mhm. So the gigabytes, I think these days memory is you can put a lot of memory, uh, hundreds of gigabytes, for example.
Yeah, sure, but in that case, they cannot share the memory. The two packages are running independently.
uh, but you can use the memory as a hard disk, like so that you
Yeah,
can, yeah,
sure, sure.
yeah.
Okay. Any other question? Well, can I have a very short elementary question? In the separation between the QM MM, geometry is completely determined from MM. So in the QM part, the geometry is just the input. Is it right?
Yes.
So for example, or if the QM part, the geometry is some kind of affected by the electronic structure the relaxation. Just the usual QMMM doesn't include that kind of relaxation. Is it right? Right?
Mm-hmm.
Okay, what I'm saying
I don't
is,
see. Yeah, I don't see your point.
so the kind of geometry is only determined by the MM part. So
It depends of the kind of techniques you are using. If you are running some kind of geometry optimization, it's always better to use some of the optimizer present in the QM packages rather than the ones in the MM packages, which are less efficient. But if you are running MD simulations, yeah, you're right. Everything is determined by the atomic positions available in the MM package. But for instance, in the coupling, the current coupling between Morcas, Open Morcas, and Tinker, actually Open Morcas, the first thing is doing is it just to ask Tinker what are the atom positions. You know, in that case, it does not have really to store locally these positions.
Okay. Thank you very much. Let's thanks the Professor Ferre.
Thank you very much.
Thank you.